Well, then I would like to welcome Joachim, who is going to give us a talk about a dependently timed drum machine language. I've been looking forward to this one very much. Please give Joachim a hand.
All right. Hi, everybody. I'm Joachim, and I'm a musician, but I'm also a computer scientist. And sometimes I like to combine the two, and a programming language is a fun way to combine things. And so that's what we're going to talk about today. When you listen to a audio signal, for instance, right now you are listening to our audio signal, it comes out of the speaker, and it's continuous in some sense. But that's, of course, not the way you perceive it. Likely you are identifying some things. Maybe you give them a name. This guy here on the image has some audio coming into his ear, and perhaps he perceives this first blue square as a hand clap, right? Or a snare drum. And likewise, when I'm producing a signal, I am unlikely to think of the continuity of things. Rather, I'm saying some words, and they have syllables, and I can put them somewhere relative to each other in time. There are various ways of describing how to put events relative to each other in time. Here is a classic one, sheet music. All right. The first, so let's say that I want to say programming drum patterns. It's likely that I will say this during the talk. Then I might use these 8 notes here. They have the same duration relative to each other, so the sentence will be programming drum patterns. Right, but that's not so close to the way I was thinking it. So maybe I'll make the 2 latter syllables a little bit faster. The note here with 2 bars is a 16th note, and it's twice as fast. Programming drum patterns. It doesn't sound that natural, but it has some effect. To fix the amount of time I spend saying my sentence, I vary the tempo by putting a little indication here of how much time is consumed, how many quarter notes is consumed per minute. That's the beats per minute. The latter one here is 4 against 3 against 3. Programming drum patterns. Neither is close to what I was trying to do when I said programming drum patterns. And it's really difficult to get it right with sheet music. Nonetheless, drummers do put their rhythms in sheet music, and here is an example. I have written a program in a programming language called BornHack that I made some time ago, and so here is the program. The program for the rhythm on the top here is this program. So let's hear it. First, we'll need to compile it, and in this prototype compiler, type checking is a little bit slow, but that's all right. In the meantime, we can inspect the type signature of the variable beat. As you can see here, the type of beat is bottom 16/16 because its duration is 16/16 notes. Can you unmute the I'll just, now that we have compiled it, it'll run a little bit faster, but I'll just run it again, this time with the audio channel unmuted. Something is a little bit overdriven. All right, you got it. And so, I mean, it's a hip hop beat, but it's not that hip. It's like a 80s hip. All right. So, but it's not uncommon to notate it like this, nonetheless. But a hip hop musician might transform what he's reading a little bit, and a classic transformation is this quintuplet shuffle. When I say classic, I mean it was hip in the hip hop scene some years ago, like 2 years. And after applying the transformation, 2 8 notes like this become, well, think of it like this. You have 2 events that happen in time, and they are kind of a family. The family of 2 rhythms is the family of things that happen with 2 durations relative to each other. After this transformation, the first note is 3/5, and the latter is only 2/5. For the sake of readability, I have overbarred the quintuplet like this. I hope you can read it. Let's do it in bottom t. So what we're doing is we are adding a phrasing here, and the first note is 3. It's a 3 against 2. And I denote it by putting a list here with a 3 and a 2. We'll just compile the song again. While we are compiling, we can inspect the type signature of the variable beat. Let's just type check in Emacs again. All right. All right. This is actually already much hipper, so I'll change the comment here. It's and express that I'm happier with it, with a smiley here. All right. The type signature of beat has become 80/80 because now it's 80/80th notes, and we'll come back to why it changed the type like that. All right. For some time, we've been developing a couple of tools for inputting rhythms into computers like this, and I want to put them into 3 categories. And the first category I will call a grid editor. On the slide here is an illustration of the beat plus baseline grid editor from Linux Multimedia Studio. There's a similar, maybe it's not called the beat plus baseline editor, but it's the same thing in Cubase and Pro Tools, and Ableton Live also has a drum machine like this. The way the program is structured is that it has 3 sequences, 1 for each signal, The lowermost signal here is a bass drum, then there's a snare drum signal and a hi-hat signal. And to input this rhythm here, which is a 8-note rhythm, we just plot in the events where we want them to happen. Alright? But if we want to do the quintuplet shuffle transformation, we can't really with this grid, because I need something 3/5 of the way through these two notes here, right? And to do so, I'll need to have a finer grid. And because the least common multiple of 5 and 8 is 40, I'll need a 40 grid. Alright? And we'll come back to that. So I need to refine the grid speculatively before I insert my rhythm into the sequencer. Another alternative is what I would like to call a signal processing language. Languages like Sonic Pi go into this category. Here I have denoted the transformed rhythm in a programming language called Choc, which was popular some years ago. Each line changes the velocity of the hi-hat channel and calls some procedures that chuck in a wave file into the signal. I have omitted these procedures in the interest of saving space in the slide. Alright, and then here I have put a comment about where we are in the rhythm. It becomes a little bit messy, and transformations on programs like this one, let's say that I had my not so hip hop rhythm and I wanted to make a transformed quintuplet shuffle rhythm, the transformation is really tedious. So it's not really feasible for a working musician to input his drum rhythms like this. Nonetheless, it is possible. Then there's a third category. I want to call the third category music score representations. And here are two examples of such representations. The first one here is a very used Haskell-embedded DSL for notating music, and it has two operators. This one here, which is the at the same time operator, and this one, which is the in sequence operator. And I have typed in here the hi-hat part for the transformed rhythm, and I play it at the same time as my transformed snare drum pattern and my transformed bass drum pattern. In C-Sound, there's an embedded DSL called DSEG, where you have an instrument that takes some patch cables, this magic DSEG patch cable, and some cables that has to be 0 and 1 all the time for some purpose, and then a patch cable that goes to the thing that outputs the wave signal, and then some canonical cables. Here is attack, sustain, decay, release. And then it takes a string, which is which represents the events that it has to produce. And the first part is the one that defines the subdivision, and here I have typed in the transformed 8 notes in a 20 grid by writing R20 out here. To summarize, we have 3 categories of ways to input rhythms into computers like this. The grid editor has some pros. The main pro, I think, is that it gives a good syntactic overview. With this grid editor, you have an overview over the whole bar, and you cannot input something that's slightly longer than the bar or combine things that will do something unexpected. On the other hand, you'll have to speculatively select a grid like this And if you select the wrong grid, you either have to turn off the grid and draw in your events by hand, which is very tedious, or you have to change the grid and start over. And furthermore, the ways that you specialize the grid in Linux multimedia system and in Cubase and in Ableton Live, which is the one I tried, is specialized for contemporary Western music. Meaning that it's much easier to separate a piece of time into two chunks of time that have equal duration than it is to separate the grid into chunks of time that have different durations in relation to each other. And finally, now we have signal processors. In a signal processor, you have full control over signals. But the way we perceive signals is in these chunks that we want to give names, and signal processing languages have poor structuring mechanisms because all of the signal processing happens at a different level of abstraction. Finally, we have the music sheet representations, and they have some pros too. My favorite pro is that it has a concise, familiar notation. For a musician, this QN variable here, which represents a quarter note, is very easy to understand. And talking about loudness, these variables here, forte and mezzo forte, are recognizable from a music sheet. But the structure of the music sheet is gone, and if one of these parts is longer than the other, then the duration of the whole thing is the duration of the longest thing, and if you combine them, you get some audio clipped out, or you get a rest somewhere, and it's really difficult to hear what the error is. It also trades off the syntactic constraints that we had in the sequencer or in the grid editor for this expressive power of expressing rhythms any way we want. It also inherits an unfortunate flaw from sheet music, that you cannot actually talk about a note by itself. So it's if you input a note into a music sheet, you cannot say a C. You have to say C for 1/4 note. So the duration is embedded into the thing that you're saying, and it has to be like that all the time. So it's optimized for reading, and it's very, that's fine if you want to give this music sheet to a person who has to read it, but it gives you some limitations for expressibility. All right, so I want to design a programming language that solved at least some of these issues. And I want it to be a declarative programming language, and I want to obtain the same kind of expressiveness that you get from a music score representation. But I also want it to be composable, and I want to separate things out. So I actually want to talk about the signal separate from the rhythm. And finally, I still want to preserve these alignment constraints that you get syntactically from your grid editor. The last part here about preserving alignment constraints is where dependent types come in. As you might notice from the title of the talk, it's a dependently timed programming language, and I'll just quickly brush that up. What I mean by a dependent type. If this is a little bit hard to follow, don't worry, but if you plan to attend the workshop tomorrow and it felt a little bit fast, it's best if you show up at 9. In the lambda calculus, all right. In the lambda calculus, here is a syntax for the lambda calculus. All right. We can have a variable, or we can have an abstraction, which is annotated by a type or a term, or we can apply a term to a term. Right? And it has some typing rules. So here's the syntax for terms and the syntax for types. It has these typing judgments, And the abstraction typing judgment is an abstraction from terms over terms, and the application rule is applying a term to a term. So clearly nothing can depend or abstract over a type in this system. One way we could decide to extend it was that we could extend the syntax for types with this type variable and then introduce a new abstraction, namely that a term can abstract over a type and a term can be applied to a type. Here's an intuition. Let's say that you have a program that takes as arguments two lists and appends them together, but it only works so long as the arguments, the elements of this list, are of the same type. So this is basically polymorphism. All right. Something else we can do is that we can let types abstract over types and just copy the typing rules for terms for types and then introduce this simpler thing that types kinds. And so now you have terms of different types and types of different kinds, and they still abstract over each other. Finally, you can let a type abstract over a term, and let's just have an intuition about this one actually. Applying a type to a type. Let's say that you have a type maybe a, and then you apply it to an integer, it becomes maybe int, right? So maybe has kind arrow, and maybe int has kind star. All right. The intuition about this one, it's you have an abstraction from a type over a term, which means that you can now apply a type to a term, and for intuition, you can apply a list to an integer and say that the type is the type of all integers of length n for some variable n in your program. And this is exactly how we are going to constrain our rhythms later. All right, an overview of the language. The primitives of the language are signals, and for now, signals are names of wave files in a folder next to the program. So the program that we just listened to, it had a folder here called samples, and the samples, they sound like this. All right, and the valid signals to talk about are the names of wave files. The user-definable parts are patterns, namely the sequence that you put into a grid editor, rhythms which relate patterns to a grid, and grooves which associates rhythms with signals. I'll make an informal introduction. Here is a program. The program has a voice. Voice is a groove, and it associates the signal hi-hat to this pattern here. The pattern has a subdivision of 4. First it divides time into 4, then it divides each part into 2, so it's 8 notes. There's also a snare voice and a kick drum voice. And for the ease of illustration, I have made a graphic that shows like where the events happen. The transformation that we performed in the BornHack program was the transformation of changing the relation in duration in between these 8th notes. We said that we repeated 4 pairs of 8th notes, and for each pair we related them in duration to each other, 3 against 2. And what BornHack did to infer the new type was to refine the grid. So instead of speculatively introducing a grid and then typing in your rhythm, you typed in your rhythm and the type system deduced which was the coarsest grid that could hold the rhythm. One final operation that you can decide to do is the one that I have denoted here, which moves a rhythm with respect to where it's notated. In this case, we move the snare drum hits a 16th note ahead, and for the sake of being instructive, we'll do this to a program. Here's a program. As you can see from the comment here, it's a white man's hip-hop program, and let's just play it. Also, let's inspect the type of beat. Beat has the type parameterized 32/16 because its duration is 32 16th notes. I'm a white guy, I like hip hop. But this hip hop is a bit 80s hip hop. And of course, when you write a hip hop beat, you want to make something hip hop. Alright? And so to make something hip hop, we can look at some rhythms. I found a rhythm that I like. Here it is. It's a samba de rota rhythm. And some years ago, the musicologist Fabian Guyon looked at some of these samba de rota rhythms. And then he noted that the swing of this tradition of music is in general to put the latter 2 16th notes of pairs of 4 16th notes a little bit ahead. Alright? So when you notate it, you want to write straight 16th notes. I'll demonstrate. Right, but it doesn't swing so well. Actually, the latter two are delayed a little bit. And I want to put this into my hip hop beat. Let's try it out. All right. To put the hip hop beat a little bit behind, we use the arrow to the little bit behind. We use the arrow to the left operator. It looks like this. And then we put it a little bit behind. Let's say we put it 1/16th note behind, 1/64th note behind. All right? And let's listen to it again. Also, let's inspect the rhythm of the type of beat. Let's type check in Emacs again. It has become 128 64th note because we need a finer grid to associate this latter 16th note with somewhere a little bit ahead. I still think it sounds a little bit white. Because Because the snare drum and the kick drum are still right on time, let's leave a little bit of space around the pulse by putting the snare drum a little bit behind the pulse and the kick drum a little bit ahead of the pulse. We put the snare drum a little bit behind the pulse by using the arrow to the right operator. This one you will have already seen before. It's type checking. Let's inspect the type of beat. Oh, it's a much finer grid. All right. Actually, now it sounds much hipper. The finer grid makes it much hipper. Now it's a Brazilian man's hip hop. And I'll change the comment out here as well because I like it. All right. There's a little bit of formalism to bottom tish as well. We'll go over that now. So just to repeat, the syntax is signals are well-formed variable names of signals. Then you can have an accent which represents loudness, and because we are programmers, we'll just represent it with a byte, so it's a number from 0 to f. And then in the rest of the syntax, I'm going to use these letters for natural numbers and Qs for rationals. A groove is either a signature that demands a duration on a groove, and it gives a type error if the groove is either too long or too short. So you can state that your groove is in 4/4. I actually think we did already. Ah, yeah, here it was. All right. So if I change the signature here, I get a type error. First, it tried to refine the grid, and it got to refine it to 320. But then it realized that to be 3/4 notes, the rhythm should be 320 note, and 240 is not 320, the compiler says. I'll agree that we can extend bottom tish to have better type errors sometime in the future. All right. A groove can also be a voice, which associates a rhythm with a signal, as we did with the hi-hat. It can be a repetition of a groove. It can be a groove played at the same time as another groove. And it can be a groove played before another groove. And a rhythm can be a subdivision followed by a pattern, or it can be a phrasing of a subdivision followed by a pattern. We did this with the shuffle transformation. It can also be a rhythm which is a little bit ahead, as we did with the Brazilian man's hip hop. It can be a rhythm which is a little bit behind, and it can be a rhythm followed by another rhythm. Finally, a pattern can be an accentuation, and a next, which is the continuation of a previous event. The reason for the annex is that when we refine the grid, we want to enforce the duration of the previous rhythm, and it can also be a rest or an abyss, or it can be the empty patterns. And the typing judgment that we use to infer the coarsest grid come following. The typing judgment for patterns is that the empty pattern is the pattern that contains no events. If you add an event to a pattern, you get a pattern that has one more event. Alright, the typing judgment for rhythms. A rhythm is parameterized with how many events and how coarse the grid. The tuplet rule states a subdivision and a pattern, and the rhythm has as many events as the pattern, but the subdivision is the product of the subdivisions. Let's say we have 8 notes which we wrote by separating time into 4 equally sized pieces and then separating each piece into 2. So computed the product of 4 and 2 and got 8 notes. Likewise, I just got a note that we have 10 minutes left, so I'll go very quickly over this one. The phrasing, of course, refines the grid enough that you can separate the grid into chunks that have the duration of the sum of whatever you separated. For instance, for the shuffle rhythm, we wanted to separate our 2 8 notes into 5 equally sized parts, right? So we multiply the number of events happening and the coarseness of the grid by 5. Moving rhythms ahead and behind doesn't change their duration. It just changes where they are realized in time. And the duration of the sequence of 2 rhythms is, of course, the sum of the events. With this extra rule that refines the grid is refined to the least common multiple of the coarseness of the 2 grids. There's also a typing judgment for grooves. A signature is just a groove which requires a coarseness of the grid and a number of events. A voice just has the same duration as the rhythm that it's associated with, and repeating a groove just multiplies the number of events by how far. Alright? And well, the sequence and simultaneous operators have typing rules very similar to those of rhythms. But you can ask me questions afterwards. Alright, now we'll have a demonstration running. And here I typed in some world music. There's a Gnawan rhythm from Morocco, an African conclave rhythm, a pulsating, it's like a reggae bass drum pulse, a hip-hop shuffle hi-hat, and a backbeat which makes everything sound a little bit more pop. And while it's playing, I'll take questions. Here. Alright, it's playing in a while because it just has to type check. We will not inspect the type of this rhythm. Alright. Coming up. Yeah. So here is the Gnawan shaker pattern. right. And while that's playing, I think it'll be playing for 3 or 5 minutes. I'll take questions if there are any.
Yeah? Yeah? Any questions?
So you have the signature statement for grooves. Couldn't you also express that by simply stating the type of the term that you have, like you would normally do in Agda, instead of having it as part of your language?
The type of signature.
So the signature term itself, it looks like it's only sort of enforcing the type.
Yes.
Yeah, but why can't you just say, for example, that beat has the type groove 4/4, and then the normal Agda type checker would sort of enforce it?
That's a good question. But you cannot. So, but I'll explain why. All right. So it's because when you state the signature, you state that it can fit into 4 quarter notes. Which will hold even though you state a rhythm which cannot be contained in a 4 grid. So 128 or 128 rhythm will still fit into the type signature of 4/4. But if you put 4/4 in the type signature, you'll get an error that 4 is not 128.
Anyone else? No? Then I think we should give Joachim a big hand for this excellent presentation.